Hi guys, so this video is going to review the life cycle of a star. So it's a TEK that we did in the beginning of the year following Cosmos. So here's just a diagram of the life cycle of a star. Every star's life cycle begins with this over here, which is called the nebula, and it is just a mass of gas and dust. And the gas and dust is spread out intensely. So think about a spider web that you get for Halloween. When it's spread out, it covers up a really large area. The spider web that you decorate, like your house or your room with. But when it's inside the package, it's packed together really tight. That would be the star. So this gas and dust pulls together really tight to become a star. Now, stars have life cycles, and the life cycle that it's going to follow, whether it be the average size or massive star, is of course based on its mass. So if a star has a small or medium mass, it's going to go this way. Okay? If a star is already a large star or massive star, it is going to follow this pathway. So before the star becomes the red giant or the red supergiant, it has to go in a phase called main sequence. Main sequence is the phase that 90% of our stars are in, including our sun. So every star must become a main sequence star before it goes down the pathway that it's going to take. So an average size star like our sun is going to become a red giant, then it'll become a planetary nebula, and then a white dwarf. A massive star is going to become a red supergiant, a supernova, and then a black hole or a neutron star. These processes take hundreds to millions of years to happen. So it's not something that happens really quick, but the stars have a life cycle just how humans have a life cycle. So the facts that you need to know is that every star must go through the main sequence phase. Every star must go through main sequence, and over 90% of our stars are in the main sequence phase. So now that we know the different phases, we're going to look at the HR diagram, which shows how we graph stars. So keep in mind the four major categories: red giant, red supergiant, main sequence, which would be what these two would be in, white dwarf. Part 7 HR diagram. The HR diagram has four categories of stars: white dwarfs, main sequence, red giants, and supergiants. And of course, you can see the size differences on the life cycle of a star picture. So the HR diagram does tell us the size of stars. It also shows us luminosity. Another word for luminosity is brightness, and another word for brightness is magnitude. So when I taught this lesson, we learned absolute and apparent magnitude. Apparent magnitude is what you think, oh, that star looks to be bright. Absolute magnitude is as if you got into a spaceship, you flew into space, and you got next to that star, and you were able to see how bright it is. So apparently, you're not listening to me. That's what I'm thinking. Absolute magnitude is if you're really doing it. I can actually see it. Another thing that's on the HR diagram is temperature, how hot the star is, and then spectral class. And we'll take a look at what spectral class is on the HR diagram. All right, so here is a basic model of an HR diagram. So instead of looking at numbers first, we're going to look at just a basic HR diagram. So On the y-axis, we can see increasing luminosity. So that means the brightness is going to increase as we go from the bottom to the top. So the dim stars are at the bottom, while the really bright stars are at the top. And then we call this section about average. So it can be bright, average, or dim. At the bottom, we have increasing surface temperature. And with this one, you need to notice that the arrow goes from here to here. So the temperature increases as you go from right to left. These are the hottest stars on this side, and these are the coldest stars on this side. This particular HR diagram does have the stars segmented into colors. However, HR diagrams are in black and white, as you can see, like this one. This one you cannot tell the color. This one is in color, but the majority of them that we are going to see on our test are like this. We cannot tell the color that a star is on the HR diagram. It depends on the model, but what you can tell every single time is size. You're always going to see them separated in these groups. They're going to be easily identified what group a star is in. So you can always tell the size, you can always tell the brightness, and you can always tell the temperature. Color is on some HR diagrams, but not all. So this line that is going through the HR diagram, this is our main sequence stars. And majority of our stars are in main sequence. They range from very cold, like down here at the bottom, all the way to really hot. I'm just going to switch to PowerPoint because this program is getting on my nerves. So here we go. You need to notice that the temperature increases as it goes this way, brightness increases as you go up, and then here are our different groups. So our white dwarfs are at the bottom. So on the temperature scale, would you describe them as very hot or cool or average? The white dwarfs are generally very hot. See, they're on this side all the way to this section right here. They're very hot and they're also very dim because they're at the bottom. So increasing luminosity is up here, right? And then dim is right here. Here's our sun. A lot of times we think that our sun is the biggest and the hottest star, but it's only because the sun is very close to us. So our sun has about an average temperature, a little bit less than average, and an average brightness. It's not at the top to be very bright, and it's not at the bottom to be dim. Here are giants. They have cool temperatures because they're on the left side, on the right side of the HR diagram. But they are pretty bright. They're about average brightness, a little bit above average. Our supergiants, they can be really cool as Betelgeuse and Antares, or they can be really hot like Rigel or Deneb. And they're all very bright. They're at the top of the HR diagram. So even though Betelgeuse is cool, it's at the top of the HR diagram, making it also very bright. Okay? So what I like to do is I like to segment the HR diagram into 4 categories. So I'm going to just draw my line down if it lets me. Maybe, maybe not. Okay, there it is. So excuse the other line right there. I'm going to erase it. So let me erase this line. All right. So stars that are in the top left, would you categorize these as hot or cool? So these stars are on the left side. Look at the arrow increasing. These stars are going to be hot. I'm going to write it the best way I can with my mouse. And now, are they going to be dim or bright? Brightness increases as you go from the bottom to the top. So these are brighter than these. These are going to be the stars that are hot and bright. to this side. So these stars, of course, are going to be hot. They're on the left side, but they're not going to be bright because they're at the bottom. So these are going to be hot and dim. On this side, these are going to be our cool stars, but they're also going to be bright because they're at the top. They're cool because they're on this side of the arrow for temperature. So these are going to be bright because they're at the top. And they're also going to be cool because they're on the right-hand side. These stars down here, they're not going to be bright because they're at the bottom. So that means they're going to be dim. And they're going to be cool because they're on this side of the temperature scale. So once we separate them into 4 quadrants, we can easily see the different categories and their temperature and brightness. So I'm going to erase all of this off the screen. And let's go to our next slide. So here's our typical HR diagram that we will be reading. Notice now that the temperature portion, of course, is in kelvins. And you can see that 2500 is over here. I'm going to just put a little circle, which is, of course, is less than 40,000. So the temperature is increasing as I go from right to left, which is opposite of what you guys see in math. Excuse my little arrowhead. I'm trying. Okay. This is luminosity, which of course is brightness or magnitude. And it is in scientific notation, which you guys have already learned. 10 to the 6th power is greater than 10 to the minus 2. So it's increasing as you go up. Our blue giants are at the top. So these are going to be really hot and really bright. Here's our main sequence. As you can see, they range from hot and bright to cool and dim. Our white dwarfs are in this bottom group. They are very hot but very dim. And then our supergiants, not very hot but very bright because they're at the top. And then our red giants, they have cool temperatures and about, I guess, a little bit more than average brightness. So they will be pretty bright. But you can also see, that, of course, that supergiants are bigger than red giants. Red giants are bigger than main sequence, and main sequence are bigger than white dwarfs. So it can tell us size. Now let's try some interpretation questions. No, let's look at this one first, sorry. Here is one that includes spectral class. Notice that the temperature is at the top now. They can put the temperature at the top or the bottom. And on this graph, they have absolute magnitude, which is the same thing as brightness, along with luminosity. Notice the bottom is the smallest number and it increases as you go up to the top. So this particular star will be in spectral class B. This particular group of stars will be in spectral class G. This group of stars will be in spectral class K. You just find the star that they're asking you to find and then run your finger down and see what spectral class it's in. All right, so here's an example. 2 stars are identified on the HR diagram below. Here's our luminosity. It also has spectral class, and temperature is at the top, still going from right to left. Based on this diagram, how do the characteristics of star 1 and 2 compare? So let's look at star 1. Star 1 is right here. Would we say that star 1 is hotter than star 2 or cooler? So star 2 has a temperature of about 7,500. Just going to draw a line from there. Star 1 has a temperature of about 20,000. It's also more further to the left. So you should know that star 1 is hotter My E is terrible, but you get the picture. Now let's look at brightness. So brightness increases as you go from the top to the bottom. As you go from the bottom to the top, I'm sorry. Star 2 has a brightness of about 1, and star 1 has a brightness of about 10 to the third power, which is more. So this star would be brighter as well. You can easily see this because star 1 is higher on the graph than star 2. So star 1 is here, star 2 is below it. So this star is hotter and brighter. So the correct answer would be G. Star 1 is hotter and brighter. Based on this diagram, which type of stars will belong to spectral class M and have the highest luminosity? Don't forget that luminosity also means brightness. We're looking for stars in spectral class K. That's gonna mean that the stars that we're looking at has to be between these two lines. But it wants the stars that have the highest luminosity. Let me make that a little bit better. The highest luminosity. Luminosity increases as you go from the bottom to the top. So our main sequence stars have the lowest luminosity, but we have some supergiants in spectral class K that have a higher luminosity. So the correct answer is J. The supergiants are at the very top of the HR diagram, meaning they are really bright, and they are also in this spectral class. If we were looking at spectral class O, it would have to be our main sequence stars up here. But you can only look at spectral class K for this question. Oh, wait. The question says M. I gotta erase all this. Sorry, guys. I don't know where I got K from. Spectral class M, Jesus. So here is spectral class M, which is in between here and here. And thank God it is still supergiants. My mistake. All right. The Hertzsprung-Russell diagram below shows how brightness, surface temperature, and color of stars are related. Which of these observations of Barnard's star is most likely accurate? So let's find Barnard's star. It's right here. So it's a part of the main sequence. It's a part of the main sequence stars. Barnard's star is less bright than the sun, which means it'll have to be below the sun, and has a surface temperature below 3800 Kelvin and is red. So our sun is about right here. Okay. Of course, brightness is here, and it is increasing as you go up. The higher you are on the top of the HR diagram, the brighter you are. So the Barnard star is less brighter than the sun because it's below it on the HR diagram. It has a brightness of about 0.01 sun, and our sun, of course, is 1 sun. It has a surface temperature below 3800, which is true because it's on the right side of 3800, and it is red. So this one is true. Barnard star is less bright than the sun. That is true. And it has a surface temperature above 3800. If it had a surface temperature above 3800, it would have to be on this side. from this line all the way back is less than 3,800. So that is not true. Barnard star is brighter than the sun. For Barnard star to be brighter than the sun, it would have to be up here or anywhere above where the sun is. And it is not. So it is not brighter than the sun. So we can eliminate C and D. And the correct answer is A. All right. Thanks for watching, guys.